Hello everyone and welcome to MB Tutors. I'm Solo and I'll be going through the first question of the physics paper that was written in May. Alright, for those who were rewriting. Okay, so without wasting any further time, I think let's just get straight to it. Please don't forget to subscribe to our channel and also please like our videos and do share this information with your fellow metric friends and those who are upgrading as well. Okay, so question 1. Okay, we're gonna go straight to 1.1. Okay, 1.1. So a bucket is at rest on a table. All right, which one of the following is the reaction force to the weight of the bucket as described by Newton's third law? Now remember Newton's third law, that's the easy one to remember. If body A pushes against body B, then body B will push against body A with the same magnitude but with the equal force, same magnitude of the force but opposite direction. Okay, I'm just really paraphrasing loosely here. So so with the reaction force, what are we going to say? Is it A, the force of the table on the earth? Well, let's just imagine this. Okay, so you have a bucket there. Okay, let's just say it has a handle, and there it is sitting on the table, and there you have the table legs. All right. Okay, this bucket has its own weight, right? And there's also the weight of the table. So the weight of the bucket, there's also the weight of the table. And these legs are also, because this is, what do they say? The bucket is at rest. So the legs are applying a force upwards, the legs of the table, and this bucket is applying a force downwards, okay? The weight, as well as the weight of the table itself. So now if A, we say force of the table on the earth, no. The force of the table on the earth is literally the weight of the table, all right? Force of the bucket on the earth, that's also like the weight of the bucket alone, so no. And then C, force of the bucket on the table, they still the weight of the bucket, but now on the table instead of the earth. And then D, force of the table on the bucket. So yes, that is the counteracting force, okay? It has the same magnitude as the weight of the bucket, but it's in the opposite direction. So definitely the force of the table on the bucket, and then the answer will be D. All right, and then 1.2. A ball is dropped. Okay, if it's dropped, the initial velocity is 0. A ball is dropped from a small height above the ground. Okay, ignore air resistance. The following pairs show physical quantities associated with the ball while it is falling to the ground. In which one of these pairs will both quantities change while the ball is falling? Okay, A. So mechanical energy is equal to what? Basically EMEC, or mechanical energy, that's equal to the kinetic energy plus the potential energy. And yes, that will I almost said it will change. If you look at kinetic energy by itself, it will change. If it was dropped, the kinetic energy is at its minimum, but as it falls and reaches the ground, the mechanical energy, the kinetic energy rather, will be its maximum. So you have a ball dropped and it, reaches the ground. So we know that initial velocity there is 0, and we know that the velocity here is at its max. All right, and then, so obviously where velocity is 0, kinetic energy will be 0, but the potential energy will be its highest there. Okay, so basically EP is at its max, okay, while EK is at its minimum. All right, and the opposite would apply once it reaches the ground. So mechanical energy in that case, it is conserved, okay? Yeah, so that will be the same, okay? Mechanical energy will be the same. But the weight, yeah, the weight will also be the same because no matter what, I mean, you have a constant gravitational acceleration acting on a body. So the weight will just be the mass times gravitational acceleration. So that'll also be constant. So A doesn't count. Then we get to B. Okay, so yeah, E mech does not count, and also the weight, which is the mass times gravitational acceleration, that won't count. Then we get to kinetic energy. Okay, I did say kinetic energy will change while it is being dropped. That's where kinetic energy is at its minimum, and there when it reaches the ground, that's where kinetic energy is at its maximum. So kinetic energy, definitely. And momentum. Okay, what is momentum? All right, momentum is basically mass times velocity. Velocity is changing, guys. We go from zero velocity because it was dropped to the maximum velocity when it reaches the ground. So definitely this works. Once you get an answer that looks correct, please don't stop there. Check out all the others because multiple choice questions can get tricky. Okay, then we have gravitational acceleration, which is G, and we know that is pretty much constant. Kinetic energy, we have spoken about it. It will change. And then lastly, D, we have gravitational potential energy. So basically, that's EP, which is equal to mgh. Okay, mass times gravitational acceleration times height. The height will change, okay? From the time it is dropped, that's where your height is its maximum, and then it keeps decreasing as you go. So this will definitely change, okay? And then we have gravitational force. And what is gravitational force? Basically, that's your constant there. We have the first mass, which is probably the mass of this ball. The second mass, the mass of the earth. And then we have r squared, which is the distance between their centers. So obviously, at the beginning, when the ball is about to be dropped, that's where the distance between their centers is the maximum, right? But guys, the force of gravity or gravitational force, it is negligible because if you think about the center of the earth is quite big. I mean, you're given the radius there in the formula sheet and the constants. It is big, okay? So in this case, the distance from the time the ball is dropped until it reaches the ground, it is negligible. You won't see much of a difference. So we don't even consider this force. So yeah, it is partly there. There is a change, but the change is quite negligible. And therefore, if we look at our strongest answer here, it would have to be B. Okay. Ooh, my table keeps making sounds. Sorry about that if you're hearing it. If you're not, just ignore my statement. Okay, 1.3. A ball is dropped from height h and strikes the floor with momentum p. Okay, let's just bear in mind, what is momentum again? It is basically your mass times velocity. So it strikes the floor with the momentum p. Okay, ignore air resistance. The ball is now dropped from height 2h. Okay, so now we have doubled the height. So what will be the momentum of the ball now as it strikes the floor? The temptation is to say, well, since the height has doubled, surely the momentum has doubled. But no, it's not really that simple. What I would like for us to do is try to get height into the equation. So right now we have momentum equal to mv. Is there a way of putting height into this equation? Because if you could, then we would substitute 2h and see if there's a difference really. And so what I propose is when you have your ball, okay, about to be dropped, and by the time it reaches the ground, remember I said here you have your potential energy being its maximum, okay? And at the bottom you have your kinetic energy being its maximum. Okay, so here when you have your potential energy as its max, you have the kinetic energy as its minimum. Okay, and as maybe let's say you take intervals, you'll start seeing that the value of the potential energy reduces while the kinetic energy increases. So basically I can make at this point at the top, EP max at the top, or rather potential energy at the top, I can make it equal to the kinetic energy at the bottom. They basically are equal. It's like trying to get the mechanical energy. Okay, so if you get the mechanical energy like at the beginning, at the top, it'll be, let's say, yeah, mechanical energy is equal to kinetic energy plus potential energy. You get 50 joules. Okay, at every point in time you keep getting 50 joules when you add the two. Okay, so therefore we can use this equation to say that the mechanical energy, no, not mechanical, the potential energy is actually equal to the kinetic energy. Okay, all right, and then what do we have then? So what is the potential energy? It's mass times gravitational acceleration times height, and your kinetic energy is half mv squared. And I think from this equation we can then get velocity in terms of height, or height in terms of velocity, and we can then substitute it into the momentum formula such that we can then put 2 times the height and see what will the momentum be. Okay, so we can cancel out the masses, and I can take g to the other side. Okay, actually let me put it in terms of velocity because that's what I really want. So velocity squared would be 2 times g times h. Okay, and if I want the velocity, it'll be square root of 2 times g times h. And remember, the equation for momentum is mass times velocity, and now we have velocity in terms of h. Okay, so basically yeah, 2gh. So this is our formula for momentum in terms of height. All right, having used the kinetic energy and the potential energy equation being equal to one another. So now I need to get the momentum when we have twice the height. Okay, so if I have twice the height, then I would have mass times 2 times gravity, gravitational acceleration, 2 times the height, because that's what I have there. All right, and then what I can then do, I would like to have something similar to the original so that I can see where the change occurred. Okay, so I will keep the 2 times gravity times the height together. Okay, and then so basically I would have the m and then square root 2gh, okay, which is similar to what I have here on the left, and then I multiplied by root 2 because that's basically what's left. Okay, remember, if you have root of something times root of something, you can put it all under big square root and multiply them inside. This is just algebra now, but yeah. And so basically the momentum would be square root of p. Okay, because p is equal to m times the square root of 2gh. All right, I hope this makes sense. I hope I'm making sense. But basically the answer there that you'd be looking at is B. Okay, all right, and then now we're on 1.4. Okay, my camera is a bit unstable. Please bear with me. All right, so 1.4. Object X exerts a gravitational force on object Y when the distance between the centers of the object is r. Now the distance r is doubled. Okay, so which one of the following represents the gravitational force that X now exerts on Y? Okay, so we know that the original equation, all right, gravitational force you have your constant, you have the mass of x, and you have the mass of y, and that's just going to be equal or over r squared, the distance between their centers. You just square that. Okay, now they're saying that the distance r is doubled. So what will we do there? Okay, everything else remains the same. The mass is the same. Okay, and then now we double the distance between their centers. All right, so it's 2r now. And if we take out the brackets, we're basically going to be left with g mx my all over 4r squared. Now what I need to do is I need to relate the original equation to the one that I currently have, okay? And what exactly has changed? Well, this 4 here in front of the r squared is the difference. So if I take that out, okay, I'll basically have a quarter there, and this will be g mx my all over r squared, and that's basically a quarter f. Okay, and where is that answer? That is A. So yeah, that's cool. All right, let's move on to question 1.5. Okay, so it says a force F moves an object P from point X to point Y along two different paths, okay, 1 and 2 as shown below. So the work done by F in moving the object is the same for both paths. Which one of the following can be used to describe F? Okay, so if we think about the normal force which acts perpendicular to your surface, if you have your object on a surface, all right, they need to be in contact, and then it acts perpendicular. All right, so normal force, I don't really think so. Tension force, well, it needs to be pulled somewhere, somehow. Frictional force would be opposing the motion, so it wouldn't be encouraging this object to move from X to Y. It is opposing the motion. But gravitational force, remember, once it's at the top, X, it has a lot of potential, okay? A high potential energy. And so gravity, which is always acting down, acting towards the center of the earth, it will force the object to move from X to Y. Okay, so I would definitely go for D in this case. Okay, and then 1.6, which one of the following can be explained by the Doppler effect? Okay, so firstly, I would like to ask you, what is the definition of the Doppler effect? Okay, so I went and wrote down the definition just to save time. But basically, with the Doppler effect, either you get an increase or decrease in the frequency of sound, okay, as the source and the observer move relative to each other. Either one is standing still, the other is moving, or both are moving, but both can't be still. There has to be some sort of movement and frequency as well, either increase or decrease, okay. And examples are, if you hear a sudden change in pitch, whether a siren is moving, you know, the sound of it as it approaches, as it is near you, and as it passes away, and also with the redshift observed by astronomers. And remember, I covered this topic of the redshift, actually even the Doppler effect. And if you don't know what I'm referring to, well, basically, if you can go to our YouTube channel and go to the playlist, you'll see we have pretty much all the physics lessons that you need there, and I do cover it, the Doppler effect as well as the blue and red shift. Okay, but getting back to our questions, I just wanted to write that down so that when you answer these questions, you think about the theory and then apply it. So it says here, which one of the following can be explained by the Doppler effect? A stethoscope is used to listen to a person's heartbeat. Okay, you might be thinking, is it possible that there's the Doppler effect there? Not really, because yes, you have a stethoscope which magnifies the sound of the heartbeat that you can hear, but there's no movement. Both the stethoscope is still, the listener, you are sitting still, the heart is connected to you, so it is sitting still too, so there's no movement there, so it's not an option. And then an echo is heard when sound waves are reflected off a cliff. Again, the thing that's moving here is the wind, okay? Echo is just, if you scream, ah, and then it keeps, whatever. Bad example. But the producer of the sound is sitting still, and wherever the hearer of the sound is probably sitting still, so there's still no motion there, okay? And thirdly, the spectrum of light from an approaching star is shifted towards shorter wavelengths. Again, what I've covered there in terms of the red shift and the blue shift. Remember, red has a high frequency, and with the high frequency, you pretty much have a low wavelength. They are inversely proportional. So there, yes, there is movement, right? There's a shift, right? And you have light as well. I know here I'm only referring to sound, but it can be light as well. It can be waves, all right? So C is an option that we can choose from, okay? And then D, sound intensity decreases when the sound source moves away from a stationary listener. So if you read that quite quickly, you'd be like, yeah, definitely D is one of the options. But here they are referring to intensity. With the Doppler effect, we are interested in the frequency. And so what's the difference like? Think about a piano. If you're playing a piano, right, and you're hitting on the keys, so the frequency of each key, right, it's pretty much the same. Whether you hit it hard or you hit it soft, the frequency is the same. But if you hit it hard, the sound is more magnified, right? And that's where we get to intensity. So basically with the frequency, if you were to draw a frequency time graph, let's say you have a certain frequency there, okay? What happens when you increase frequency? If you were to increase frequency, then you're gonna have a lot of waves, okay, per second or whatever. What happens then when you increase the intensity of the sound? Well, basically your frequency still stays the same, but your amplitude basically increases, okay? And in that case then the frequency is not really affected by the intensity. It stays the same regardless. So in this case, the redshift will work. That will be an example. Okay, so we go with C. And then 1.7, we're almost there. Two oppositely charged point charges move towards each other. Okay, if they're oppositely charged, one is negative, the other is positive. Obviously, there's a force of attraction between the two. They should be moving towards each other, right? Now it says, which one of the following is correct? The point charges move at a constant velocity. No. They can't be. Think about, okay, so point charges are very small, okay? But to understand it on a bigger scale, think about taking two magnets, all right? Maybe bar magnets where you have the north and south pole, and you're attracting the north and the south pole. Okay, not the north and the north because they will repel. If you start and you like put them together, my thing is unstable. If you were to have the two magnets, let's say these are the two magnets, and they are quite apart, right? The closer you get, the bigger the force of attraction, and they will like come closer together. I don't know if you've experienced that, if you have played with but again, balls of steel that have magnets inside, and they attract quite quickly. So in this case, constant velocity cannot be the answer, because constant velocity says they come gently to each other and they mix, and no, that's not the case. Decreasing velocity, no, the velocity is increasing. If they're going to attract and come close to each other, the velocity is definitely increasing. Constant acceleration, is it constant? Is it accelerating? Is it increasing? Sorry. So the answer is between C and D. Now let's just use a formula to help us with that. Okay. So as these point charges are moving towards one another, their velocity will increase. So there is acceleration. So we agree on that, right? And the force between them will get even stronger. Now, if we use Newton's second law in equation form, we know that the force is directly proportional to acceleration. So the higher the force, or when the force increases, so will the acceleration, or if the acceleration increases, so will the force, because they are directly proportional, right? But acceleration is inversely proportional to mass. That is what Newton's second law says. So in this case, we are definitely expecting an increase in acceleration. The acceleration is not constant because the force is not constant, and because they are directly proportional to each other, your answer will be D. And then 1.8. Which one of the following phrases describes the EMF of a battery? Okay, a loose definition that I'm going to give with regard to the EMF is basically you get your maximum voltage in a circuit when there's no current, okay? Because as soon as you close the switch, or current starts moving around the circuit, you are going to lose some volts, okay? There will be some lost volts out there. And so the EMF, if you were to measure the voltage, it won't be the maximum, which is the EMF. So EMF for me is maximum, okay? But let's look at the options given. So it says the energy supplied per unit time. If you have energy, okay, so if you have energy over time, okay, that's basically when you have power, and we normally write it as power is work per unit time. All right, so that's not really describing EMF here, okay? And then B, charge transferred per unit time. You know that if you have charge per unit time, that's basically the current. That is not the EMF. The current affects the EMF, all right? Or rather, in the circuit, if there's current, then you have some lost volts. EMF never changes. EMF is always the same, all right? But the reading on a voltmeter would change as soon as current is there. But current does not describe the EMF. It affects the reading of the voltmeter. C, current supplied per unit charge. Yeah, not really sure about that one, but that doesn't sound right. So the charge is supplying the current. Okay, yeah, that doesn't make sense. But anyway, D, maximum energy supplied per unit charge. So basically energy again. So we have energy, maximum energy supplied per unit charge. Okay, I will then say, we can translate that as work per unit charge. That would be equal to voltage, right? Yeah, I think that would be equal to voltage. I think if we checked the formula sheet, we can see if there is an equation there that talks about that. Okay, so we have work is equal to the voltage times Q, small q. So if we have, so basically voltage can be equal to work over Q, right? Because work is equal to voltage times Q. So we can definitely go with that. Where were we? 1.8. So maximum energy supplied per unit charge, yes. So if your work is at its maximum, then the voltage will be at its maximum, and therefore we can say that it would be the EMF of the battery. Okay, so we can go with D for 1.8. And then 1.9, we're almost there. Or are we? The graph below represents the output voltage versus time for an AC generator. Okay, alternating current. That definitely looks like a sine graph. So it says the speed of rotation of the generator's coil is now doubled, right? Which one of the following, or which one of the combinations below shows the correct new peak output voltage and the time for one rotation? Okay, so this reminds me of Faraday's law, and I'm just gonna, yeah, so Faraday's law, we need to now, I'm gonna write down the equation and then we're gonna discuss it, because we're talking about the speed of the rotation of the generator's coil being doubled. I think that is, yeah, that is being doubled, but let me just write it down. So the equation there would be EMF. I don't know if they have it there, just so that you should know whether you should know it off by heart or it's there provided in the paper. Okay, let's just, no, it won't be here at the beginning. Electrostatic, electric circuits. Okay, we don't really have the equation, so I guess you have to know it because this was covered in grade 11. Right, so to answer this question, you need a little bit of understanding of Faraday's law, and then you're gonna have to apply some knowledge, just making sense of all the theories that you know and try to get an answer. So Faraday's law of electromagnetic induction says whenever a conductor is placed in a varying magnetic field, an EMF is induced. And as such, you can see that the EMF is equal to the number of loops multiplied by the magnetic flux per unit time. Okay, so the number of terms, you have a negative in front there. So what they're saying here is the speed of rotation of the generator's coil is now doubled. Okay, so this number of turns, or the loops, okay, so as a turn, it's now doubled. Okay, so basically you're gonna have 2 times there of that whole equation on the right hand side of the equation sign. And since now the EMF is doubled, remember the EMF currently here, that's the maximum voltage, right? EMF is currently 200, okay? So if we double it now by the speed doubling, then we're gonna have 400, okay? So in the peak output voltage, A and B, no, A. Okay, so yeah, basically, if you figured out that the EMF is doubled, which is 400, then I guess you'll go with A. But let's just say there were more options for 400, né? And let's see for the time for one rotation. So currently, the time for one rotation, which is the one full wavelength, okay, that's basically going to be 0.04 seconds. Okay, I hope you can see that. I can't at the moment edit this PDF, but yeah, so this is basically one wavelength, one period, if you may, if you're used to the terminology from the sine graph. Okay, and the time it takes for one wave to be completed, as you can see in the graph, it is 0.04 seconds. Okay, and now we're wondering, if you increase the speed, how will that influence the time? In my mind, if things are done quicker, the wavelengths should get, a little bit shorter. All right, but we need to show how do we, get to that conclusion. I hope you remember that the speed is basically equal to the wavelength times the frequency. I hope I'm quoting the correct formula, but yeah, it should be that. Where are these things? Where is C? Yes, speed. Actually, let's not use C, because C is the speed of light, right? So V, velocity or speed, is equal to the frequency times the wavelength. And what do we know? We know that the frequency and the wavelength are inversely proportional. So if you increase one, you decrease the other. Okay, so let's do it this way. If I wanted to get the frequency, I would say that it would be the speed over the wavelength. So we can see that indeed frequency and wavelength are inversely proportional, but frequency and speed are directly proportional. So if you are going to increase the speed, you will increase the frequency. And if you increase the frequency, okay, so instead of one wavelength happening over 0.04 seconds, if you increase the frequency, well, you might have many wavelengths, but we don't know really how many. So yeah, so how can I then relate frequency and time? Well, we do have that equation. I think it's somewhere here. Yes, the period is basically equal to 1 over frequency. And if speed and frequency are directly proportional, if you double the speed, you double the frequency. Okay, so what happens to the period over there? Basically, it will be halved. Okay, so if it took you 0.04 seconds to complete one wavelength, then once it is halved, okay, it will then become 0.02 seconds instead of the 0.04. And let's see, crossing fingers that that is what the time is. And yeah, that is what the time is. So basically you have reached a new peak, okay, because the EMF was doubled. So now you have 400 volts, and instead of one wave being completed in 0.04 seconds, it will basically be completed in 0.02 seconds. So it will be something like that. Okay, 0.02, and therefore the answer would be A. But like I said, if you figured out that the EMF is doubled, there was absolutely no need for you to check the time. Okay, and 1.10, a photon of light of energy 2x joules is shone onto a metal surface with work function x joules. Now it says, which one of the following represents the maximum kinetic energy in joules of the electron ejected from the metal by its photon? Okay, so you know that kinetic energy, or the maximum in this case, is basically equal to half mv squared. But we do not have the mass, nor do we have the velocity, so we can't exactly say what the maximum kinetic energy is using this equation. But if we consult again the formula sheet, yeah, we basically get that the energy, okay, is equal to the work function plus the maximum kinetic energy. Okay, and what do they tell us about the energy as well as the work function? I believe they did give us information. Well, they said that the photon energy is 2x, okay, and that the work function is x. So we can definitely work out the kinetic energy, or the maximum kinetic energy would basically be x. Okay, and that is option C. And guys, that's it from me with regard to question 1. Yeah, not a smooth one, technical glitches and everything, but I guess we made it. If I was not explaining something well enough, please do comment below and I'll try to give a refined, better explanation. All right, that's what happens, I guess, when you record at night when you should be sleeping. But thank you for tuning in. I hope you learned something. I hope that this will be a good preparation for your coming exam. All right, bye. Hello everyone and welcome to MV Tutors. I'm Tolo and I'll be doing question 2 with you guys. Please don't forget to like our videos and subscribe to our channel and also spread the word. So yeah, let's get to it. So it says, a man faces difficulty while swimming in a dam. During the rescue operation, an inflated tube attached to a helicopter by a rope is dropped from the helicopter. Okay, initial velocity 0. The man, of mass 70 kilograms, holds onto the inflated tube of mass 4 kilograms while the helicopter is flying horizontally at a constant speed. Okay, so acceleration, 0. An average frictional force of 300 Newton is exerted on the man-tube combination while they are dragged horizontally along the surface of the water by the helicopter. The rope makes an angle of 50 degrees with the surface of the water, as shown in the diagram below. Assume that the rope is inextensible and massless, and the water of the dam does not flow. Ooh, if it flowed. Anyway, let's start with the question. So 2.1, state Newton's first law of motion in words. Okay, guys, I'm going to state it. You're going to write it down, okay? So question 2, in particular, 2.1. Basically, Newton's first law is like the law of inertia, all right? And what is inertia? What does the law say? Let's just get to the question. The law says a certain body will move at a constant speed, or it will remain at rest or be stationary unless an external force acts on it. And this external force must not be equal to 0. Of course, why would it be equal to 0? Like, it would be, it wouldn't make a difference. So, but yeah, they want you to state that. So, a body will remain at rest or move at constant velocity along a straight line unless an external force is exerted on it. And that external force must be equal to 0. Okay. And then you get your 2 marks. Then, 2.2. Okay. Draw a free body diagram of the man-tube combination while they are being dragged. Okay, so this is the man on the tube, I'm supposing, or holding onto the tube while they drag them along the water. Okay, and now we're going to draw the free body diagram. Okay, let's do this. So this is the man and tube combination, and obviously the first obvious arrow we're going to put is weight. Okay, and this will be the weight of the man plus the weight of the tube. Okay, and if you wanted to write down the values, they didn't ask for it. Yeah, they just said free body diagram, so you don't really need to put the values. But if you wanted to, it would basically be the 70 plus the 4 times 9,8. Okay, then the second obvious force vector we're going to put there is the tension force. Okay, yeah, tension force. All right, so I don't know if you guys in class write FT or just put it as T. Even here, I don't know if you put it as FG or W. Okay, so whatever it is that's accepted, do that. And then because the motion is to the left, friction will always oppose motion, okay, or else it's not friction really. So you're gonna have a component of friction, all right? So force of friction, and that friction is kinetic friction, all right? And then, you know, because the body, or rather the man and the tube, the man-tube combination is in contact with the water, all right? So there'll be a force from the water, okay? And therefore we need to have the normal force, all right? If there was no contact at all, then we wouldn't have the normal force. So I would put the normal force there, okay? In terms of the, yeah, so even here, I don't know if you put Fn or you just put N. And here, do you just put FK? It's really up to you. What was I saying? In terms of the arrows, ideally you'd like to show that the force of friction is not really bigger than, if we were to resolve, so this is 50 degrees, right? If we were to resolve the tension force in its components, basically, okay, at this point, what I'm putting in purple, I don't think you need to put when you draw the free body diagram. So this is just me adding extra information, but this would be T cos 50 because, you know, the angle is adjacent to the arrow. And you'd also have another force here, T sine 50 degrees. Okay, so you would like to show that the tension force, or the x component of the tension force, is bigger than the friction force, or else if they are equal in size as you draw them, then it means this person is not moving. Okay, so just be aware of that. Like I said, I don't even know how strict they are in terms of the lengths of of the, yeah, so I would put friction force like slightly less. Okay, so I don't know how strict they are, but just be aware of that. Okay, they didn't say we should draw it to scale, so as long as you show the friction force, the tension, the force of gravitation, and the normal force, then we're good to go. Now 2.3. Now we need to calculate the tension in the rope. I'm going to look at my sketch, and looking at the horizontal is way easy. I'm going to calculate the tension in the rope using the horizontal forces. I don't want to deal with the vertical because it gets a little bit complicated, especially with the normal force. Okay, we have unknowns, quite a few. So yeah, so now we know that the resultant force, or F net, is equal to mass times acceleration. And because this plane or this helicopter is moving at a constant speed, there is no acceleration. Okay, so we already know that this is going to be 0. And then if we look at our free body diagram, and if I take the left as positive because that's the direction of motion, you can take the right as being positive. It's really up to you. But I will have T cos 50 as positive, and I will subtract the friction force. Okay, and so basically T cos 50 would be equal to the friction force, and T, so the friction force, they told us it is 300 Newton. So we have 300 all over cos 50 degrees, and your answer will be in Newton. Okay, because we are calculating force, and that's the tension force. So we have 300 all over cos 50, and we get 466,72. Okay, 466,72 Newton. All right, so far so good, ne? Yeah. Now 2.4. It says, how will the answer to question 2.3 change if the helicopter accelerates while dragging the man? The frictional force and the angle between the rope and the surface of the water remain the same. So we need to choose from increasing, or increases, decreases, or no change. So basically now, okay, so our resultant force, okay, is equal to mass times acceleration, and this time there is acceleration. Okay, so again, this time T would be equal to force of friction plus mass times acceleration, and all of that would be divided by cos 50. So before we only had the force of friction divided by cos 50. Now we have the mass and the acceleration plus the friction divided by cos 50. So definitely it will increase. Okay. And if they ask why, this is why. We just showed using a formula and an equation. We don't really need values. We can see that the force of friction added to the mass and the acceleration will result in this value increasing. The tension in the tension in the rope will increase. Okay, and that's 2.4. All right, and then last question, 2.5. Okay, so in another rescue operation, the inflated tube of mass 4 kilograms is dropped from the stationary helicopter. Okay, so now the helicopter is stationary. Okay, and this tube has been dropped. So still initial velocity is 0. And it strikes the water at a speed of 60 meters per second. Okay, the tube sinks vertically downwards into the water. to a depth of 0.8 meters and then rises to the surface. So there is no tension because the rope hangs loosely. All right, now calculate the magnitude of the average force or the average upward force exerted on the inflated tube while it is sinking. Assume that the average upward force is constant for the motion. Okay, I'm gonna just sketch this out, what's actually happening. So we have the tube now. Let's see, this is indicated by the tube, and then it falls, right? Falls all the way into the water. So we had initially 0 meters per second because it was dropped. All right, and then now we have the water there. So once it got to the surface of the water, they said that the speed was 16 meters per second. Okay, and then now it went under the water for a depth of 0.8 meters. Okay, and if there was no upward force from the water, then it would have remained there. But because the water is like, foreign object, go back to the surface. Okay, so let's say the tube is there. Okay, there is an upward force, okay, force of the water that is causing it to go back to the surface. Okay, but also this has its own weight. Okay, actually I should have drawn it the other way around. If this were to be a free body diagram, I would say the force of water is causing it to go up to the surface, but its own weight it's causing it to go down. So basically, a twisted version of Newton's third law is that the weight is it's not really equal. At this position, the weight and the force of water is not equal because the force of water is greater, it will take it up. All right, they will only be at equilibrium at the surface of the water, because at the surface of the water, even though you still have the weight, you do have the force of the water keeping it there. So there, Newton's third law is fine. All right, but what are they looking for? They're looking for that force of water. All right, so we're going to go back to Newton's second law, where we say the resultant force is equal to mass times acceleration. And what is this resultant force? Well, it depends. What are you taking as positive, upwards or downwards? I'm going to take upwards as positive. Okay, so if upwards is positive, then basically I have the force of the water minus the weight of the tube being equal to mass times acceleration. So what do I have? What don't I have? I have the weight, I have the mass, I'm missing the acceleration, and I'm looking ultimately for the force of the water, the upward force. And so we need to get the acceleration. And if you're not sure which formula to use, I would consult the equations of motion. Remember, equations of motions are not limited only to free fall. Okay. One thing I also forgot to say. So it was dropped, right? So the initial velocity is 0 meters per second. Then it reaches its maximum velocity when it touches, or when it reaches the surface of the water, which is 16 meters per second. But do you realize that as it sinks, as it goes down, the speed decreases until it reaches this point where it is 0 meters per second, okay, until it goes back up again. All right, so we are going to take the motion, we're looking basically at the motion of it going down, touching the water, and it sinking. We're not looking at it going up. All right, so what do we have? The information that we have is basically the depth beneath the water, and we also have velocity. And if I look at the equations of motion, 75% of them have time in it. So the only one that doesn't have time is this one. The final velocity squared is equal to initial velocity plus 2 times the acceleration delta y. Why? Because it's vertical motion, not horizontal, so we're not going to use delta x. Okay, and so Yeah. So now we can get this acceleration. And it's not g, okay? This is not free fall. So please don't use g. Now that we have our equation, we need to substitute, okay? So let's have a look. Scarf is falling off. So our final velocity there, if we're going to take the motion of it sinking, remember we chose up as positive, right? So the motion of it sinking is going down, right? So our final velocity there is 0 squared. Our initial velocity, because starts with 16 and it starts slowing down. Okay, so it'll be negative 16 there squared. Then we have 2 times acceleration, but this acceleration though, it's kind of slowing down, right? But it's still, sinking beneath the waters. But yeah, it definitely is slowing down. So you put negative a there. And then our delta y, well, that's going to be 0, 0.8. And if you're not sure about that, if you're not sure about the sign, remember it's going to be the final depth minus initial depth. Initially, we had 0, and finally, we have 0, 0.8. Okay, so that's basically going to be 0, 0.8. And now we can solve. If I take 16 squared to the other side, okay, it's going to be negative 16 squared. And then I'm left with negative 2 times 0, 0.8, which is 1,6a. And so acceleration will be equal to negative. No, it won't be negative. Can we just get what 16 squared is? Okay, it's 256. So I have negative 256 is equal to negative 1,6a. Okay, so acceleration, it will be 256 divided by 1,6. And that's basically 160 meters per second squared. Does that make sense? Does it make sense? Well, if this tube is falling inside, right, it is basically decelerating before it reaches 0. Started off at 16 meters per second, and it's busy going down, so it is decelerating. And because we chose upward as positive, if you think about it, once it reaches this point of 0 meters per second, okay, remember we had 0 because it was dropped, then this was the maximum as it touched the water, and then it reached 0 before it went up again. So this was, in this direction, we have deceleration in the downwards direction, but in the upward direction, it will be acceleration, and that's why we have positive there, I guess. So now that we have acceleration, we go back to our equation where we had the force of water minus your weight, okay, is equal to mass times acceleration. And now force of water, which is what we're looking for, would be mass times acceleration plus the weight. We have our mass, which is 4 kilograms, and then our acceleration is 160. Then we have the weight, again 4 times g, and because we've taken up as positive and g is actually down, this will be negative 9,8. Okay, and if we work it out, we have 4 times 160 minus 9,8 times 4, and we have 600,8. Just gonna say 0.80. So that's quite a big force there. Okay, so yeah, I guess we are done. Thank you for tuning in. Again, if you have any concerns, any questions, I know I sometimes am very guilty of making silly mistakes. Please do correct me in the comment section. There's always room for growth, improvement, correction, and I don't mind it. So thank you for tuning in, and that's it from me. Ooh-wee. Hello everyone and welcome back to MV Tutors. I'm Tilo and I'm looking at question 3 with you guys today. Alright, you know the drill. Please don't forget to like our videos, to subscribe to our channel, to share this information with someone who might need it, someone in matric, someone who's upgrading. You know, sharing is caring. Oh my word. I've been talking so much. Now I'm burping, sorry. Question 3. All right. So a small disk C is thrown vertically upwards at a speed of 15 meters per second from the edge of the roof of a building of height 30 meters. You can see that in the sketch. After 0.5 seconds, a small ball B is shot vertically upwards from the foot of the building at a speed of 40 meters per second in order to hit disk C. Okay, so ignore the effects of air resistance. All right, 3.1. Okay, so it says explain the term projectile. All right, I am not going to write that down, but I'm just going to say it. So a projectile, it is an object. All right, it can be a stone, can be a ball, can be a bullet, whatever. It is an object, okay, that is either thrown or dropped or shot or whatever. All right, and then the force that will act on it over its motion will be gravity. Okay, and again, if you would like to get more knowledge on vertical projectile motion or projectiles in general, you can have a look at our videos here. We do describe it in detail. We go through the vertical projectile motion of a dropped projectile, of a thrown projectile, of a bouncing projectile, and that infamous question of the hot air balloon that the matric saw last year after a very long time. And yeah, so let's get back to the question. So basically that is a projectile. Now we can get to the calculations. Okay, the fun part. So it says calculate the time taken by disk C to reach its maximum height. Okay, so we know with disk C that the initial velocity is basically 15 meters per second. No? And we know that the final velocity, which is when it reaches its maximum height, that will be 0, okay, meters per second, because now it needs to change direction. It went all the way up, reached its maximum, and now it needs to go back down. And then what else do we know? What are we looking for again? We're looking for the time it takes. Okay, so this is our unknown, and that is the time. So we'll be looking at the equations of motion and basically where we need the time, where time is factored into the equations. All right, what else do we have? Yeah, we can shoot straight to the equations. Okay, so which one will we use? We have initial velocity, we have final velocity. Oh, we need to decide, are we taking up as positive or down as positive? Let us take down as positive. Why not? Okay, so I would take the first equation over here. All right, it's quite simple and straightforward. So we have that the final velocity is equal to the initial velocity plus the acceleration times delta d. And because we're looking at vertical projectile motion, A will be g, all right? And since we are taking downwards as positive, g will be positive. So our final velocity is 0. All right, and then our initial velocity is 15. Remember, it goes up. So because we've taken downwards as positive, this will be a negative 15. And then g will be positive, okay, because downwards is positive. And then our unknown is t, time. So then delta t, this table, can I just keep quiet? Okay, so delta t will be equal to 15 over 9,8. So how long does it take this projectile to reach its maximum height? So 15 divided by 9,8 is 1,53 seconds. Okay, I'm gonna pause and fix this table. Okay, and then 3.2.2, it says calculate the maximum height above the ground reached by disk C. Okay, so we know the time it took for it to reach its maximum height. Now we need to go and check out the time, the height. Okay, we have the time, now we're gonna calculate the height. So 3.2.2, which equation are we gonna use now? All right, so we have the final velocity, we have the initial velocity, and we're going to choose this equation. Okay, so final velocity squared is equal to initial velocity squared plus 2g delta y. And why am I going for this equation? Well, in the event that your time that you calculated in 3.2.1 is incorrect, we need to get an equation that is independent of time, if possible. Okay, so since we have the final velocity, which is 0, and the initial velocity, which is minus 15, we can definitely calculate for delta y. Okay, 2 times 9,8, 9,8. All right, and we have delta y. So if I calculate for delta y, it will be equal to, I'm just trying to do the algebra in my head. So I'm going to have 15 squared, negative 15 squared, and I will have, this answer will be negative. Why? Because it's going up, right? The delta y will be, I don't know if you get me when I say it's going up, but it is going up. So we're going to get a negative y, but we'll see how we mechanic this thing. Because if you take this whole term to the left hand side, it will be negative. Okay, so then we're going to divide by 2 times 9,8. All right. And then, yeah, so 15 squared. So you have 15 squared all over 19,6. But let's just put it in 2 times 9,8. And we get 11,48. Okay, negative 11,48 meters. Okay, which just means it's upwards. So the actual magnitude is just 11,48 meters. But that is not what they asked. They didn't ask from the top of the building to the maximum height. They actually asked for the maximum height above ground, not above the building. So if we have 30 meters, okay, and this is all above ground, and then we have an additional 11,48, what will the final height above ground be? So that plus 30, so that's 41,48. So therefore the answer is 41,48 meters. Okay, and yeah, that should be it. All right, now we're going to look at question 3.3. Okay, it says calculate the time from the moment that disk C was thrown upwards until the time ball B hits the disk. Okay, so for all the visual learners out there like me, you want to just see what's actually happening here. So if I were to draw a displacement time graph, I need to see what's actually happening. So here at 0 seconds, that is where disk C is, right? Then it goes through its projectile motion. It doesn't actually reach the ground because ball B ends up hitting it at some point. We don't know where, okay? But we do know that disk C reaches its maximum height at 1,53 seconds. We do know that initially it had a velocity of 15 meters per second. There it was 0 meters per second. What else? Yeah, so that's what we know about disk C. But with ball B, it says that after 0,5 seconds, then ball B is shot vertically. Okay, so let's say that was, okay, so that's 0,5 seconds. This is where ball B is, okay, and it is shot up, right, at initial velocity of 40 meters per second. And we're not sure exactly where on the projectile of disk C will ball B shoot it. Okay, so we can guess, for example, that it could have shot it at that point, but not really. I mean, it just left at 0,5 seconds. So I'm just going to assume here, and the calculations will prove if the assumption is correct. I'm going to assume that ball B actually shot at disk C somewhere after disk C had already, it started going down. It had already reached its maximum height and now it's on its way down. Okay, and at this point, we really don't know what the time is, nor do we know what the height is. Let me actually use H. Okay. Yeah. Oh yeah, we can actually use Y. H or Y, it doesn't matter. Okay, and that's basically what we are looking for at this point, but we're looking at for the time. Okay, the height is not really an issue at the moment. But let's see, what are we going to do and what do we know? So for disk C, I know that the initial velocity is 15 meters per second, but because we chose downwards as positive, I'm going to have to choose negative, or rather make it a negative 15. I also know that the time it takes is t seconds, right? And also the height. Okay, let's look at the height. Let's say this is where we are, right? And that is height h. What does height h consist of? It consists of the 30 meters plus the delta y. So if we were going to calculate what delta y is, you would take it from this position here, and that would be your delta y. Okay, I hope you are understanding there. So if I were to put this equation in terms of delta y, I would say h minus 30, and you'll see why I want to put it in terms of delta y. So that is disk C. Now we can have a look at ball B. Okay, what happened with ball B? We know that the initial velocity for it is 40 meters per second, but because it's going up, it has to be negative. Now, what about the time? Okay, I know that B, or ball B, is lagging by 0,5 seconds because when disk C is about to be thrown up, ball B was still relaxing. Only after 0,5 seconds did ball B become, start its motion, basically. So if disk C is at 1 second, we know that ball B is at 0,5 seconds. So there's that lag of 0,5 seconds. So we need to take account of that, okay, and subtract t, or rather subtract 0,5 from t, okay? And when it comes to the height of ball B, so let's say ball B has to go and, intersect there with disk C's motion. Yeah, so basically that will be the delta y. The reason why we added 30 with disk C is because it started at that point, 30, and went up. But with ball B, I mean, it's starting at 0, so it's just delta Y. Okay, so our H there would be delta Y. And then I think we can start. So how exactly are we going to do this? It looks like we're going to be solving simultaneously. And I need to use an equation from the equations of motion where I don't need the final velocity, or I don't have to use final velocity because I don't have it for both of them. I just have initial velocity, I have the displacement, and I have the time, right? And actually all the equations, not all of them, half of them use final velocity, but the one where it incorporates delta y, t, and initial velocity is the top right equation. So basically I will be using this equation. Delta y is equal to initial velocity times t plus a half acceleration, which will be just g delta t squared. And I'm going to have an equation for each, okay, for disk C and ball B. And so if I look at disk C, so delta y is basically h minus 30, if I could say. And what is that h? This would be the h, all right? And yeah, so I have delta y is equal to initial velocity times t. Actually, let me just plug in the values. I know that the initial velocity is negative 15 times t plus half of 9,8 is 4,9 t squared. Okay, this is my first equation. And then for ball B, again I have that, I forgot the 30. I wrote it up there and now I'm forgetting it here. It's actually negative 30. Okay, and then here delta y, I have negative 40. But remember t, we have to subtract 0,5 seconds. And then I have again 4,9 because a half times 9,8 is 4,9. And then instead of just having t squared, it'll be t minus 0,5 squared. Okay, and there is no 30 there that we're adding or subtracting. So if I were to simplify this, I would get negative 40 times t plus 20 plus 4,9. And in here, I have t squared minus t plus a quarter. Okay, so this is the maths portion of it. Algebra. I hope you're good at that. Yeah. And then we have 4,9 t squared minus 4,9 t plus 4,9 over 4. I'll figure it out later what it is. And so I can equate both equations, right? And that's why I wanted to write it in the form of delta y. So I have negative 15t plus 4,9 t squared minus 30 is equal to, let me just add what I can add. So I have negative 44,9 t, 20 plus 4, okay, now I need to work it out. I can't delay any longer. So I have negative 40 minus 4,9 over 4. Okay, and that's negative 41,225. Negative 41,225. I did the wrong thing here. I'm supposed to add it with 20, not negative 40. Okay, so it will be 20 plus. Alrighty. Okay, can't get rid of this negative. Okay, let me just start over. So I have 20 plus 4,9 over 4, and that's 21,225. Okay, 21,225, and then I'm left with 4,9 t squared. Okay, so once we get here, I can see that I can actually cancel out 4,9 t squared, and I can take the 44,9 to the left side, and let's see what would I have. So if I had 44,9 minus 15, I have 29,9 t. And then if I take 30 or negative 30 to the right side, I have 30 plus 21, that's going to be 51, and then I have 225, and if I take 51, okay, we're going to divide both sides by 29,9, and then finally I have 51,225 divided by 29,9, and that's 1,71 seconds. Okay, so yeah, getting back to the question, just to see, are we done? Do we need to do something else? But yeah, it said calculate the time from the moment that disk C was thrown upwards until the time ball B hits the disk. So in our sketch, okay, so we have now the value for that time, which is 1,71. Okay, 1,71, and we have a particular y value there. And if you want to work it out, you can take the time and pretty much substitute it in either this equation or that equation, whichever one is simpler for you. But they're not asking for the height at which they collide, or ball B actually collides into disk C. They just wanted the time, which is 1,71. Ooh. Okay, 1,71. All right, yeah, 1,71, and that's basically it. All right, yeah, we will continue with the other question. Okay, and then yeah, so 3.3, the time was 1,71 seconds. So ball B will hit disk C just after disk C has reached its maximum height, and it's coming back down. All right, so let's see, now 3.4, it says on the same set of axes, sketch graphs of velocity versus time for disk C and ball B from the moment that disk C was thrown upwards until ball B hits disk C. Okay, so I'm just going to put some timestamps, right? So we know that at t is equal to 0 seconds, that is when the velocity for C was negative 15 meters per second, because we've chosen down as positive. All right, and then at t is equal to 0,5 seconds, we know that the velocity for B is actually negative 40 meters per second. Okay, out of curiosity, what would the velocity for C be? So basically we have the time, we have the initial velocity. Now we can look at the equations for getting the final velocity, and we can use the first equation, right? So final velocity is equal to initial velocity plus g delta t. All right, so initial velocity was negative 15. Okay, and we have 9,8, and the time 0,5. So let's just see there. We have negative 15 plus 9,8 times 0,5. So we have negative 10,1. Okay, that was just out of interest. All right, and then let's have a look. What else do they want in this graph to be shown? So we have the initial velocity for ball B and disc C, and then the time at which ball B was shot upwards, so that was 0.5 seconds. The time at which disc C reaches its maximum height, so we know that that time we calculated it was 1.53 seconds, and we know that the velocity there for C was 0 because it had reached its maximum height. Out of curiosity, what is the velocity for ball B? Well, we're going to use the same equation. We know that the initial velocity was -40, and the time that we are interested in is 1.53 seconds. So at that point, B is -25 meters per second. Okay, what else do they want to know? The time at which ball B hits disc C, and that time is 1.71, which we just calculated. So out of curiosity, what would the velocity be for C, and what would the velocity be for B? What are we expecting? Okay, if we look at the graph I drew before, so because let me use a different colored pen. For C, okay, it had gone up until it reached the maximum, and that's why it was negative, the velocity that is. But now that we're going down, I'm expecting this velocity to be positive. On the other hand, for ball B, it's still going up until it reaches the disc. Okay, so I'm expecting the velocity for ball B to be negative. But let's see. Let's just test our theory. Okay, still using the same equation. So we have the initial velocity for disc C as 15, -15, and then the time there that we have is 1, yes. All right, so the velocity there would be 1.76 meters per second. And then for ball B, initial velocity is -40, and there we have -23.24. So all the negatives just tell us that in actual fact, the velocity is 23.24, but it is pointing upwards. Okay, so all the negatives show that it is headed in the upward direction. So I think we can, or we are in the position to sketch the graph, velocity time graph. We have quite a lot of negative velocities and just one positive. So yeah, that should give us an indication of how we should use our axes. Okay, so we have velocity here on the y-axis, and then we have time in seconds. Okay, so we have 0. What intervals should I use? 0.05. No, 0.5. And then we have 1, 1.5, and 2. Okay, so I will use red for, or maybe green for C. Okay, and then we said at 0 seconds C was -15, so I'll just put -15 there. At 0.5 we had -10.1. Okay, this is not going to be to scale, but yeah, -10.1. And then at 1.53 we had 0, so somewhere there we have 0. And then at 1.71 seconds we have, I'm just gonna put it there. Yeah, like I said, it's not to scale, so we have 1.76. Okay, 1.76, and then we're just gonna plot. Ooh, definitely not to scale. but let's see what we can do. Okay, so I'll have to adjust my dots. Okay, so we'll say that's negative 10 comma 1, and we'll say that is 1 comma 53, and that will be 1 comma 76. Okay, so that is for disk C. And now what would the plot look like for ball B? So at 0 seconds it was not yet in the mix. Okay, so we're gonna do it now. At 0 comma 5 we had negative 40, so I'm just gonna put it somewhere here. All right, and then at 1 comma 53 it was negative 25, so somewhere there I suppose. And at 1 comma 7 1 seconds we had negative 23. Okay, so not so far off. Negative 25, now we have negative 23. So yeah, it didn't really move by much. And yeah, let's draw somewhat of a straight line there. Okay, maybe we can expand it a bit, extend it. Okay, and this value here is negative 40. Yeah, so it only, I think this is how I should look. I'm wondering now, what should I put here? But let's just leave it because it was not even in the picture at that time. And I think, okay, before I let you go, I'm realizing that my graphs actually are not looking that proper. I know I said I didn't draw it to scale, but the one thing about drawing the velocity time graph, especially more than one graph, is they have the same gradient, okay? And because they have the same gradient, they should be parallel to one another. And because with ball B, okay, if you look at the scales, it doesn't make sense how this would be 15 and then I have here 25 and I have here 23. So yeah, just an error that I would like to rectify before we call it a day. Okay, these graphs have to be parallel because they have the same gradient. Even if you don't draw it to scale, it should be reflective of that they are parallel. Okay, so let us just fix. All right, so at this point here, okay, so we have negative 40 at 0.5 seconds, and then at 1.53 seconds we had negative 25. Okay, that makes a whole lot of sense. Okay, so negative 25, and then at 1.76 seconds we have negative 23.24. Okay, so I think that is a little bit better now. Okay, yeah, so that is it from me. Remember, more than one graph on the velocity time graph, they have to be parallel to one another. Noma kanjani. Okay, bye.
Well, hello there. Welcome to MV Tutors. My name is Ferrashe Manana, and we're still doing paper 1 of physical science. Okay, 2022 May June examination. This was your supplementary examination. You just wrote this if you were upgrading, but if you are watching this in order to help you to to study further for your exam, then you came to the right place. Well, without any further ado, let's get into it. We're in question number 4 now, and the first question says, what is meant by an isolated system in physics? Okay, that's cool. We can jam that. So we're on question 4.1, right? So let's just write that. An isolated system. An isolated system, okay, is a system, right? First of all, it's a system that has no net external force. Okay, it has no net external force, meaning the net external force is 0. Okay, but also what it does mean is that energy is conserved. But not only energy being conserved, but also momentum is constant. So there's no outside external forces that are involved here, so the energy is conserved and also momentum is constant because there's no external forces disturbing it, so it's isolated. Okay, now let's read this. Now, during an experiment, a rocket of unknown mass is mounted on a toy cart. Okay, I see it over there. Good. Of mass 20 kg. The cart rocket combination moves at a constant speed of that 2.5 meters per second along a horizontal floor. Thank you. At a certain instant, the rocket is fired horizontally in the direction of motion at a speed of 30 meters per second. As a result, the cart slows down to a speed of 0.6 meters per second, as shown in the diagram below. Ignore frictional effects. So when they say ignore frictional effects, this is then an isolated system. Okay, because they're telling us to ignore external forces, and that is why they were asking us even here 4.1 what is meant by isolated system, because they want us to understand that we're about to do a question on isolated system, which means we are going to ignore all external forces. The net force is 0. Alright, so 4.2 says use relevant physics principle to explain why the firing of the rocket will slow down the cart. Okay, let's do that. I want to change color though. I want to use, let's go blue. Okay, so this is 4.2 now. Okay, so according to, how do you spell according? Is it like this? According to Newton's third law, okay, when two bodies interact, Okay, what happens? They apply forces to one another. They apply forces to one another that are equal but opposite. That are equal but opposite. Okay? That are equal but opposite. Full stop. Therefore, which is defined in Newton's third law. Therefore, when the rocket, when the rocket is fired, okay, what happens? It, okay, applies a force that is equal but opposite to the cut. So this means that as it moves initially with this 30 meters per second, it applies this 30 meters per second equally but opposite, okay, to the cut, and there, and thus, let me say, thus slowing it down. Okay, so it applies the same 30. Remember, it was moving at 2.5, and then it applies the 30, and then that slows down the cut to 0.6. That's it. Okay, and the next question says, calculate the mass of the rocket at the instant the rocket was fired from the toy cut. Okay, we're just calculating the mass of the rocket. We will use the principles of momentum to do this. Okay, let's just get some space. Let's change the color so that we are dynamic. Let's go black this time. So we are now on 4.3. Calculate the mass. Okay, so let's use, according to momentum principles, the momentum before an isolated system should be equals to the momentum after. Okay, so what's the momentum before? Do you see that before the rocket is fired, after the rocket is fired? So what we're gonna say, before the rocket is fired, we have them together. So we have the mass of the cut plus the mass of the rocket. And actually, I want to start with the rocket. Let's do that. I want to say the mass of the rocket plus the mass of the cut. Okay, they are together, and they are going on the same initial velocity. Okay, that's what's happening before, but afterwards there's a separation. We have the mass of the rocket and its velocity, its final velocity, plus the mass of the cut and its final velocity. Alright, so let's do this now. Let's put values. What's the mass of the rocket? That's what we're looking for. The mass of the cut we are given here, it's 20 kgs. so we'll just put that 20 over here. And the initial velocity we also given right over there, okay, 2.5. That's going to be equals to the mass of the rocket, which we don't know, but its final velocity, there it is. Once again, it's 30 plus the mass of the cut is 20 times the final velocity is 0.6, just like that. Okay, now we just have to do some mathematical gymnastics to solve the mass of the rocket. So we'll multiply that in. We'll have 2.5 times mr plus 2.5 times 20. That's going to be equals to 30 mr plus 20 times 0.6. I'm going to put the mr's in one side and the values on the other side. So this side I will have 2.5 times 20. If I bring this side, it's going to be minus 20 times 0.6, and then this side I will have 30 mr minus 2.5 mr. And then to solve mr, then I'm just going to say I want to put this in a calculator. It's going to be 2.5 times 20 minus 20 times 0.6 divided by, this is 30 minus 2.5. Alright, let's get a calculator and see what that actually gives us. I'm going to put a fraction, and then on top I'm going to put 2.5 times 20 minus 20 times 0.6. Then I come downstairs, I got 30 minus 2.5. My answer is that 1 point, so mr is 1.38 kilograms. Very small. Remember, it's a toy in any case. Well, that's it for this question. Do hope that you understood everything that we did. Other than that, please do like and subscribe to our channel if you liked this content. It will help you to get more content from us as we keep posting, and also help others receive it. Other than that, that's it for me. Enjoy your day. Well, good day to you. Welcome to MV Tutors. My name is Pilagashi Manana, and we are still doing the 2022 May-June examination for physical science, paper number 1. And we're now on question number 5. If this is what you're looking for, then you came to the right place. Stick around. At the end of this, I'll show you. You will understand how to do this question. Okay, let's get right into it. So it says, an arrestor beds or arrestor beds. Well, first of all, what are arrestor beds? Okay, so you have a truck coming down. Arrestor beds are just there on the road to slow down vehicles, usually trucks. So it has to be very, very, very high in friction, because it has to slow down vehicles, especially trucks. So arrestor beds are used to help moving trucks to come to a stop when their brakes fail. Exactly what I just said. The driver of a 30,000 kilogram truck driving down a steep road drives onto an ascending arrestor bed inclined at 28 degrees to the horizontal as shown excuse me, as shown in the diagram below. There we go. It's coming down. It needs to slow down. There is an ascending arrestor bed there. So first question says, states the work energy theorem in words. Okay, we'll do just that. 5.1. Okay, so whenever they ask you this question, I'm sure you know by now since you've studied that there's a formula in your formula sheet that is that's like this. The network is equals to change in kinetic energy. So this is exactly what you have to describe in words. So you have to say the work energy theorem states that the network done by forces on an object are equal to the change in kinetic energy. That's it. That's all. Let's move on. It says the truck with failed brakes passes point A, okay, at the beginning of the arrestor bed at a speed of 33 meters per second. That's important. The average frictional force on the truck is 31,000 newtons while the truck moves up the arrestor bed. Ignore the rotational effects of the wheels. Give a reason why the network done on the truck while moving on the arrestor bed is negative while moving up. Okay, so for this one, what I would like to do, right, is let me change that to red. First of all, let's delete that S. First of all, I want to draw the free body diagram. So we've got that incline there. There's the horizontal, and then we've got the truck right there, just moving up. Right. So what are the forces acting here? We've got the weight of the truck, right, moving like that. Okay, I actually want to write it this side. Okay, it's just the weight. And then what we do have is, if we were to resolve this weight into its components, remember the motion is going that way. Okay, so perpendicular to the motion, we have the weight component that is perpendicular, and then parallel to it, then we have that motion going that way. So this is the weight that is parallel component of the weight. Cool. So motion is going up, right? Okay, I don't want to show it per se, but this is just to demonstrate that the motion is going up, which means friction then is going the opposite direction. So we've got the force of friction like that. Okay, so now the question says, give reason why the net work done on the truck while moving on the arrestor bed is negative. Remember, the motion is going up. Friction is going opposite, which is negative, and the weight as well is contributing towards the negative direction as well. Okay, meaning that we can then conclude that, well, what is happening here is that friction and the parallel weight component weights component act on the opposite direction of motion. Of motion. Then thus, that's what they said. Moving, why the net work done. Thus, the net work done on the truck is negative. Okay, that's the statement they wanted us to prove. All right. Okay, let's move on. 5 point, where are we? 5.3. Use energy principles to calculate the minimum length of the arrestor bed needed to bring the truck to a stop. Okay, energy principles, that's what that's the operative word right there. We have to use the energy principles. So let's come back here. Let's go through this time. This is now 5.3. So energy principles, what do we know? The one that we remember, these questions are leading on. We have to use the work energy theorem. Okay, and remember, if you check your formula sheet, you'll find this formula that the net work is equals to the change in kinetic energy, like that. And then what is the formula for work? The formula for work is just F change in X and cos theta. Okay, that's in your formula sheet. If you check it, it's there. And then formula for kinetic energy, as you know, is half mv squared. So we're gonna suit it for this particular question. Now, what are the forces that we have? We have, if we look at our free body diagram over there, well, let me just redo another one because I don't want to keep scrolling up and down. What we have is that we've got the weight going down, obviously, and then we've got its components going that way and that way, and then we've got friction. So we've got friction, and then we've got, I just want to write down the relevant ones. The parallel, and then we've got 28 degrees there. 28 degrees right there. Okay, just a small diagram. So let's go with let's start with friction. So we've got the force of friction, the change in distance, and then we've got cos theta. The cos theta of friction, remember motion is going that way, so this is 180 degrees. Okay, and then what else have we got? Plus we've got the weight, okay, the parallel weight. Now I just want to solve that parallel weight. What do we know? Okay, if we say the parallel weight is, if we say sine 28 is equals to the parallel weight over the actual weight, then we will have that the parallel weight is actually equals to the weight sine 28. And what is the weight? The weight we are given here is mass times gravity. The mass of the truck is 30,000 times its gravity, which is 9.8 sine 28. Okay, so that's what I'm gonna write here. Okay, so when it comes to the weight component, let me just put it like this here. Parallel weight, its change in x, and then cos 180. Okay, that's the friction side, that's the force side. Okay, because it's also acting at 180. And then that's equals to, if we go to the side of the what you call the kinetic energy, we're gonna have half the mass of the truck, which is 30,000, times, first of all, we'll start with the final velocities. I'll just call it the VF because it's the change, minus a half times 30,000, which is the mass, and it's VI. Okay, and then now let's give ourselves more space. That's gonna be equals to, okay, force of friction. Let's start there. What's the force of friction? Were we given force of friction? Let's see. Where is it? Ah, yeah, there we are, 31,000. So we've got 31,000. It's a force of friction times the change in x, and then cos 180. If I put this, I just know it's -1. So I'm just going to put that plus the weight parallel component is, I'll write it just like that, which is 30,000 times 9.8 times sine 28, and then we've got the change in distance, and then cos 180 once again is -1. Okay, so that's equals to, if I put this in a calculator, oh, it's going to be, well, taking out the common factors, which is half of 30,000, that's 15,000. And then my final velocity, remember it has to come to a stop, which is 0, minus my initial velocity I've been given is 33. And remember, these are squared. Don't make the mistake of forgetting that this is squared. Okay. When I was defining it up there, did I put it squared? Yes, I did. So this is squared. Alright, now all I have to do is just mathematical gymnastics, where I will have this side I will have minus 31,000 change in x minus that one. Let me just put it in a calculator real quickly. It's 30,000, just to clean it up, times 9.8 times the sine of 28. Okay, so then I will have that number, minus 138,024.6395. I'll write the whole number because I want to be as accurate as possible. Change in x. Cool. And this side, what am I gonna have here? Let me just put it. It's 15,000. Whatever, it's gonna be minus because of that negative. So it's 15,000 times 33 squared, and it's that number 16,335,000. Okay, so it's like that. So you see, this is one side, that's another side, and then from the then the change in x then is just going to be equals to that, or rather this, which is 16,335,000 divided by let me restore the negative for consistency's sake, 31,000 minus 138,024.6395. Okay, that's what I gotta put in the calculator. Okay, I'll put it like this in fraction form. So it's negative 16,335, 3 zeros. Here it's negative 31,000 minus 138,024.6395. Okay, what do we get? 96.64. So that's the change in meters. That's the change in calculate the minimum length. That's the minimum length of the arrested bed. So obviously they'll make it longer than that because they want like maximum impact. So 96.64 meters. Cool. The next question says the diagram below shows the same truck entering a descending arrested bed. Inclined at 28 to the horizontal, the initial speed of the truck and average frictional force in the truck are still 33 and 31,000 respectively. Which arrested bed, ascending or descending, will be able to stop the truck in a shorter distance? Explain the answer in terms of forces acting on the bed. Okay, so under scenario 1, we do know and we have established this that that's okay, let me just say 5.4. We've established under scenario 1, when it's ascending, that you've got the weight because motion is going that way, then you've got friction going that way. But now that it's and then also this component is going that way. Okay, we've established that, but under scenario 2 now, where it's descending, we have motion is going that way, so friction is going the opposite way. It's going up, and then we've got the weight, and then if we resolve the weight, then the parallel weight is moving there. This time it's moving down with the motion. Okay, so you see you got two opposing forces when it's ascending, whereas here you've got one opposing force, which is the friction, whereas the weight component is going down with the direction of motion. So then we can conclude and say, well, it looks like it's definitely going to be the ascending one. That's our answer. Because as you can see, friction and parallel weight act opposite. Because friction and parallel weight act opposite motion direction. Okay, opposite motion. While in the descending only friction acts opposite motion. Okay, but that's not enough just to say that. You have to qualify it. Okay, so I will say thus, the greater the force, the greater the distance required. So this is the force acting on the direction of motion. The greater the force on the direction of motion, the greater the distance required for the truck to actually stop. That's it. That's all we have to say. Well, I hope you understood. But please do, if you like this content, please do like and subscribe to our channel so that you can get future uploads. And also, well, that's it from me. You do enjoy the rest of the day. I appreciate you. Well, welcome to MV Tutors. My name is Philagahle Manana, and I will be doing this paper with you. We are now in question number 6 of the physical science May-June 2022 exam. Okay, this is the supplementary exam, and if this is what you're looking for to prepare for your test or exam, then you came to the right place. Okay, without any further ado, let's get right into it. Question 6 says, let's read together, a car moves at a constant speed of 10 meters per second towards a stationary sound source. So it's very important to distinguish between the source and the listener. So that's the source right there. Oops. That's the source, and then that's the listener, just like that. Okay, and then it says the sound source emits sound waves of a frequency of that. Okay, the sound detector A is attached to the car, and another sound detector B is attached to the source sound, the sound source. Detector B detects the sound waves reflected from the car. The speed of sound in air is 340. Okay, that's a standard one. Question 6.1 states the Doppler effect in words. Okay, let's do that. That's 6.1. Doppler effect in words says that the change. Okay, so the change in the observed frequency, okay, of a wave the change in the observed frequency of a wave when the source moves relative when the source moves relative to the transmitting medium. So this is just saying the frequency changes as the source and the listener move relative to each other. For example, an increase in frequency of the sound wave as the source and observer moves towards each other. There's an increase, or there can be a decrease as they move towards each other. That's just a Doppler effect. Anyway, this is just theory. Let's get to the calculation. It says calculate the wavelength of the sound waves emitted by the source. Okay, so now in your let's change the color. Let's go blue. So in your for six, this is now 6.2. In your formula sheet, you will find the formula V is equals to F lambda. Okay, and we know, you should know by definition now that lambda is the wavelength that they're looking for, and it's equals to V over F. And what is our velocity? Now this is they said calculate the wavelength of the sound waves emitted by the source, and we've been told here that the speed of sound in A is 340. It's just a standard number. Standard. You should know it by head here, even if they don't give it to you. And then the frequency that we've been given, the source sound emits a sound wave of frequency. There we go. There's the frequency there, 880. So we've got 880. Let's get our calculator. Okay, so we've got 340 divided by 880. That's equals to that. We've got an answer of 0.386 meters. Did they say anything about the decimal points? No, nothing. Okay, so anyway, that's the That's the wavelength they wanted. Now 6.3, calculate the frequency of the sound waves detected by detector A. Detector A, remember we said this is the listener. Okay, so now when we go to our formulas, let's go red. When we go to our formulas, we're gonna have 6.3. If you check your formula sheet, you're gonna see that the frequency of the listener is equals to V plus or minus VL divided by V plus or minus Vs. We'll put this in the bracket times Fs. Okay, but now what's the scenario? Because we have different scenarios when it comes to these things. Okay, the scenario that we have here, if we look carefully, what's happening? The car is moving, which is the listener is moving towards. Okay, so listener, how do I spell listener? Moves towards source. And what we know that is that if a listener moves towards source, then what we have is that we must add VL. Okay, we add VL. Therefore, our final formula will be V plus VL. Okay, all over. Well, Vs is gonna be 0 anyway. That's the velocity of the sound. Remember, this sound source is the source is stationary, so its velocity is just 0. So I'm not gonna include it in this formula. Okay, let's put in numbers. That one there is 340 plus velocity of the listener, which here we are told is 10 meters a second, and then this one is still 340. All of this must be multiplied. The frequency of the sound source, frequency of the sound source, we are told is 880. Okay, then all we have to do is put this in a calculator. Okay, so let me open the bracket, put fraction. We got 340 on top plus 10. At the bottom, we've got 340. Let's go to the side. We close that bracket. We multiply everything by 880. 880. And then our final answer is 905.882. Good. And then what are the units here? We're talking about hertz. Good. Okay, let's go to the next question. It says the sketch graph below shows the frequency recorded by detector A. So detector A is that of the listener, right? Let me just say frequency of listener. Detector recorded by detector A. Redraw the graph above for detector A in your answer book on the same axis, the same set of axes. Sketch the graph of the frequency recorded by detector B. Label this graph B. Okay, so what are we gonna do here? Let me just expand this. B is that of the source. Now, if you think about this, the frequency of the source, because remember the source emits, okay, do you expect it to be bigger or smaller? Okay, I would say the frequency of the source should actually be bigger because the frequency of the source is highest at the source. Okay, so let me just put it that way. Let me just put it that way. So then in drawing, I'll just use this one. So then I would put it over here, right over there, like that, and that's going to be a label that B. It's on top. That's it. Oh, okay. Well, that's it. That's it from my side. I hope you understood everything we did. Please do like and subscribe to our channel. Would appreciate this, and I do appreciate you doing this and watching this. Well, enjoy the rest of your day. Well, welcome to MV Tutors. My name is Firagahle Manana, and we are doing the 2022 Supplementary Exam, Physical Science, Paper 1. We're now on question number 7, and if this is what you're looking for, then you came to the right place. Stick around, and at the end of this, you will know what exactly to do with this question. Well, without any further ado, let's get right into it. It says, two small identical spheres P and T are placed a distance 0.1 meters apart, as shown in the diagram below. P carries a charge of 3 positive 3 times 10. This is just microcoulombs, and T carries a charge of negative 3 microcoulombs. Okay, I can see it there. This one is negative, that's positive. State Coulomb's law in words. Let's go ahead and do that. That's question 7.1.1. Coulomb's law states that, well, for Coulomb's law, first of all, let's just get the formula. You get it in your formula sheet, which is F is equals to K Q1 Q2 over R squared. So you're basically just describing this relationship with Coulomb's law. So then we can therefore say that Coulomb's law states that the magnitude of the electrostatic force, we have to know how to use the exact words, that electrostatic force. It's not just any force, it's the electrostatic force between two charges, okay, is directly proportional. It's directly proportional, okay, to what's this? The product. To the product of their charges, and inversely proportional to the square. As you can see, it's the square of the distance the distance between them. Between them. Okay, that's it. And then now this one says draw the resultant electric field pattern due to the charges on P and Q. Okay, so for this one, right, what we have here, let me change to blue. What we have here in 7.1.2 is that we have a positive charge, right, and a negative charge. Okay, so what happens to the electric field? I do have a simulation I can show you here. If you have a positive charge, do you see that electric field is going away from it? Okay, and then if I have a negative charge, do you see that electric field is going towards it? So now in the scenario that we have here, we have a negative charge and a positive charge. So you see what's going on? The electric field is going away from positive towards negative. So this is exactly what we have to draw. So we're going to say what we saw that we do that. We saw that the charge was going from positive to negative, and we saw that it goes away from the positive, and we saw that it goes towards the negative. Okay, so you can just add more for aesthetics looks, you know, so that it looks much better, but something like that, good enough. And then now let's go back to the question. It says a third charge sphere S of unknown charge QS is placed a distance of 0.15 meters from sphere T, such that the three charged spheres are at the vertices of a right angle triangle. Okay, that's cool. So if it's right angle, we can use Pythagoras to find the net force. So the net electrostatic force on sphere T due to the other two charged spheres has a magnitude of 10 newtons. There, they've shown it. It's shown in the diagram below. Is charge QS positive or negative? Okay, let's see what's going on here. So what we're going to do, this is now what's this, 7.1.3. let's see what's happening. So we've got a positive charge there, okay, and then we've got a negative charge there, and then we've got this one that we want to determine. What we know is that this charge here, which is negative, is attracted to this positive one, so it moves up like that. And also what we know is that the resultant one is moving like that. Okay, it's showed there. Okay, so now we have to determine which distance is this one gonna go. Okay, we're gonna use the head to tail method. Okay, so we move from the head and we go to the tail. Okay, or rather from the head to the tail. So what we do is that to get to that resultant there, we have to go this way, right, and we go up to get there. this one is the same as that one in any case. So do you see what happened? If it moves towards it, there's a force of attraction there. And that means for it to be attracted, for a negative to be attracted, it means this one has to be positive. Okay, so therefore we're going to choose is the charge QS because this is S, this is QS there, is positive. Okay, it would have been negative if the resultant was going down, so that we do the head to tail, then you'll know that it's repelling. But since the negative is moving towards the positive, then it must be attractive. That's making it positive QS. Okay, now it says calculate the number of spheres added. Calculate number of electrons added to or removed from sphere S to give it a charge QS. So what do they want here? They want the number of electrons, right? Now if you check your formula sheet, you will notice that actually the we're now on 7.1.4. you notice that the formula that you need to calculate the number of electrons in your formula sheet is N is equals to Q over E. Okay, so that's QS in this example. So we need to solve QS, right? How do we do that? Because we know that the number will be given by this equation. So to solve QS, where we can start, we can say, okay, we can use Pythagoras, okay, to get that charge. So we are going to say, we're working backwards now, we're going to say the resultant force, or the net force, according to Pythagoras, squared is equals to the force of, I'll call it T as they did, the force of T on P, okay, squared, plus the force of so T on P plus the force of T on S, or we can say S on T and the other way around. Okay, but let's leave it like this. So with the net force, we know it's 10 squared because it's given right over there, and then now T on P, T on P, did you calculate it somewhere? No, doesn't look like there was a question that wanted us to calculate it, but we can calculate it because we have all the variables for it. We know that it's going to be, we'll use that formula which is K Q1, we have the value of Q1, Q2, we have the value of Q2 over the distance between them. In this case, it's QT over and QP here. Okay. and all of this has to be squared plus ft on s squared. Okay, so we'll need to, solve that. So now we're gonna just do some mathematic gymnastics, but before that, let's put some values. What's the value of k? K is 9 times 10 to the power 9 times qt. Qt is 3 times 10 minus 6 times qp. Qp is also 3 times 10 to the power minus 6, and this is all over. The distance between them is 0.1, so it's going to be 0.1 squared plus ft on s squared. Okay. Oof, it looks nasty, but let's bring in a calculator. 10 squared, let me just put it right now, is 100. Cool. And then this one, I'll put in a fraction on top. It's 9 times 10 to the power 9 times 3 times 10 to the power of negative 6. Come down, times 3 times 10 to the power negative 6 again. It's all on top. Downstairs it's 0.1 squared, and I get 81 or 8.1. So I get 8.1 this side. Plus ft on s. This is still squared. Okay, and then now what I'm gonna do, all we have to do is simply bring this side. 100 minus 8.1, that's gonna be 91.9 equals to ft on s squared. But if I just want ft on s alone, then I have to do the square root on both sides. Let's check that out. So I'm gonna say oh, remember okay, yes, the 8.1 is squared. Okay, so let's rub all of that. Can't just subtract it. It must be, because all of this must be squared. 8.1 squared, it must be squared, so there must be a square here, right? Because it's Pythagoras. Good, don't make that mistake. So this side then will have 100 minus 8.1 squared is equals to ft on s squared as well. And if I take the square root of both sides, then that should give me my answer. Okay. Let me put that in a calculator. It's 100 minus 8.1 squared. And then I get 5.864. So therefore, the force of T on S is equals to 5.864. Let me just take 3 decimal places, and it's a force of attraction, right? Okay, so now that I have the force, I can solve QS, because that force of T on S is equals to K QT QS and the distance between them. So that force, I've just solved it, is 5.864 is equals to 9 times 10 to the power 9 times QT. Do we know what QT is? Yes, we do. It's 3 microcoulombs. 3 times 10 to the power minus 6 times QS, which is what we're looking for, divided by the distance between them has been given right there, 0.15, and it must be squared. Now we're just going to do some mathematical gymnastics really to solve for QS. I'm going to take all numbers to this side, so it's going to be 5.864 times 0.15 squared, cross multiplying, divide by this one here, which is 9 times 10 to the power 9 times 3 times 10 to the power minus 6. All of that is equals to QS. Left with QS. Therefore, QS will then be equals to, let me put this in a calculator, fraction, let's go 5.864 times 0.15 squared, and then I'll come downstairs. I have 9 times 10 to the power of 9, come downstairs, times 3 times 10 to the power, put a negative 6 there. So QS is equals to 4.887 times 10 to the power negative 6 coulombs. There. Did they say anything about how many decimal? They didn't say nothing. But since they gave us 2, well, we could put 2, which is fine, but the more the merrier as well. 3 is fine. Anyway, that's our answer right there for QS. But remember, they wanted the number of electrons, so we're not done. The number of electrons then will be QS over E. Okay, remember E is a constant for a single electron. So 4.887 times 10 to the power minus 6 divided by E is given by, if you check your formula sheet, it's 1.6 times 10 to the power minus 19. Let's put this in a calculator. Fraction, we got 4.887 times 10 to the power negative 6. Come downstairs, we go 1.6 times 10 to the power negative 19. Wow, what a big value. But anyway, the number of electrons is 3. Let me take it at 2 decimal places. 0.5 times 10 to the power 13. That's the number of electrons. you only really required to put units on your final answer. So while you're working it out, you don't need to put units. So essentially, I didn't need to put units here because that was not the final answer. Okay, so in a sense, I had to remove that and that. Okay, because that's my final answer right there. Cool, let's go to the next question. Let's do question 7.2 now. Let's just change the color of this pen. Let's go black this time. It says P is a variable point in the electric field of a charged sphere A, and R is the distance between point P and the center of sphere A. See the diagram below. So there's sphere A, that's the distance, that's P. A learner determines the magnitude of the electric field at point P for different values of R. Sphere A is then replaced by another sphere B of a different charge. Another set of results are obtained. The graphs below are obtained from the results of the sphere A and sphere B. EA, that's the energy, is the magnitude of electric field. Oh, it's electric field, my bad. At a distance of 0.04 meters from the center of charged sphere A. Okay, use the graph to answer the following questions. State the proportionality between the magnitude of electric field E at a point and 1 over R squared. Okay, so this is question 7.2.1. So they want us to state the proportionality between EA and, or just E, doesn't have to be A, and 1 over R. They want us to state the proportionality between these two. But here's the tricky part. You must take this as one thing. Okay, 1 over R squared is one unit, it's one entity. And as you can see, the more we increase the more we increase on the X, the Y also increases because the graph is going up. Okay, so which means an increase on an increase is always a direct proportionality. So then we will say, therefore, E is directly proportional. Proportional to 1 over R. They didn't ask for R alone, they said 1 over R squared. Okay, there we go. And then calculate EA if the numerical value of the gradient of the graph for sphere A is 680. Okay, we've got a gradient now. Let's go green. So we've got a gradient now. This is now 7.2.2. Okay, and then we know that the gradient is equals to the change. Is it change in y over change in x, or x over y? I think it's a change of x over the change of y. We'll leave it like that. Okay, we'll leave it like that, which is change of x, change of y. Okay, we would be wrong if we did that. It's the change in y over the change in x. Okay, you must always correct your wrong answers. So the gradient then therefore is given as, it says here, with a point of magnitude E. Okay, proportion. Calculate the numerical value of the gradient of the graph for sphere A is 680. So the gradient is 680. And how calculate EA? EA is as you can see, is on the Y. So that's the change in Y, and the change in X. Calculate the numerical value of the gradient. Oh, oof, guys, I'm tired. I've been doing this paper today, so I'm getting answers wrong. I'm getting values actually mixed up. Okay, so let's try again. Calculate EA if the numerical value of the gradient of the graph. It is the gradient. Why am I being confused? 680 is the gradient, and we're looking for EA, but the change in X we're given, there it is on the graph. It's 1 over 0.04 squared. Okay, and we just have to solve EA. So EA is equals to, we'll do cross multiplication, 680 times 1 over 0.04 squared. Let's put that in a calculator real quickly. So we got 680 times a fraction. It's got 1 on top, and at the bottom it's got 0.04 squared. And we get that number, 425,000. Okay, and then what are the units? Well, you don't have to guess them, they're written there. Newtons per coulomb. 7.2.3 now. Okay, how does the magnitude of the charge on sphere B compare to the magnitude of the charge on sphere A? Choose from greater than, smaller than, or equal to. Give reason for your answer. Give a reason. Okay, so what I'm gonna do here is that I'm just gonna, for the same 1 over r squared, we can see that we're gonna, that's sphere B right there. We can see that we have a greater E value. Okay, so that's EB. All right, so what is the relationship then between E and the charge? The relationship is that they are directly proportional. So the greater the E value, the greater the charge. So then we can say then this side, it's going to be greater than, because E is directly proportional to Q. Where do we get that from? We get that from Coulomb. Here it is here. Yep, there it is. The charge. There. Remember when we did this? You can see that directly that's the magnitude of the electrostatic force, which is pretty much the magnitude of the electric field. So they are directly proportional with Q, as you can see there, meaning if they're directly proportional, If you increase one, the other increases. So it's greater than because E is directly proportional to Q. That's it. Well, I hope you understood that. Um, I do appreciate you, and please do like and subscribe our channel. It will help others to get this content as well, but also you will get our future uploads as we continue to upload these videos. Other than that, that's it from me. Goodbye and enjoy the rest of your day. Well, welcome to MV Tutors. My name is Firarashe Manana, and we are still doing the 2022 May June Physical Science Paper 1. Okay, we are now on question number 8, and if this is what you're looking for, then you came to the right place. Let's get right into it. Now, it says in the circuit below, a battery of unknown EMF and an internal resistance of 0.5 ohms, that's important, we will need it, is connected to two resistors, 8 ohms and 5 ohms, right? And 4 ohms and 8 ohms each, and a resistor R of unknown resistance. Ignore the resistance of the connecting wires. Cool. The three external resistors are ohmic conductors. Explain the meaning of the term ohmic conductor. Okay, let's get into it. So 8.1, which is going to say, first we're gonna say Ohm's law because it has to do with ohms. Ohm's law states that there is a linear relationship. There's a linear relationship between two things. What are they? Voltage and current. Okay, so full stop. Let's put a full stop right there. So conductors that follow this law are called ohmic conductors. So all I did here, I just had to define what Ohm laws says, and basically what I'm saying now is that ohmic conductors are just conductors that obey Ohm's law. But then I had to define Ohm's law for you so that you see the connection. And then it says 8.2, when switch S is open, there it is, S is open, voltmeter V1 reads, so V1 is over there, it reads 3.2. It reads 3.2 volts. Okay, cool. Calculate the current through the battery. What do we know about current? Because this is in series. If it's open, okay, it's in series. So what do we know about current in series? Current flows like water, so you know all the water flows through here. Okay, so basically what we can say, current is the same throughout the wire, doesn't change. Okay, so the same current that's passing through this 4 ohms resistor is the same everywhere. Okay, so what we are going to do then, let's go back. what we're going to do for 8.2.1 is that we're going to calculate the total current using the resistance and the voltage that we've been given over there. Okay, so I like to draw my triangle. V is always on top of the triangle. Okay, and then I got IR there. So when I'm looking for I, as in here, I'm gonna say I is equals to V over R, and the voltage is 3.2, and the resistance is 4 ohms. Okay, let's get our calculator. We're gonna say 3.2 divided by 4. There we go. 0.8. 0.8 amperes. That's our total current that is flowing through the wire when the switch is open. Okay, and then it says calculate the EMF of the battery. That's cool, we can do that. Let's go blue this time. So now this is question 8.2.2. EMF formula, if you check your formula sheet, is given by current, okay, times resistance, because remember EMF is like voltage, so it's like saying voltage is equal to current times resistance. But here EMF has to do with the battery. The battery has an internal resistance as well, so it's not just the total resistance. Okay, so current, we've just solved it to be 0.8. Resistance, the total resistance in series is 4 plus 8, so we got a 4 ohms plus the 8 one, and then we're going to add the internal resistance of 0.5, which we've been given over that side, 0.5. okay, then that's what we're going to put in our calculator. Let's do that. So it's 0.8. Then I've got two brackets. This one has 4 plus 8, close that one, and then plus 0.5, close that one, get 10. So my EMF is 10 volts. Okay, 10 volts right there. Okay, let's move on. When switch S is closed, so switch S is closed now, so the current can flow. It's closed over there, so that means the current flows over there as well. Okay, now it says calculate the resistance of resistor R. Oh, and it's 5 marks. That's a long one. They want us to get the resistor R, which is that one. So we're gonna have to work a little bit backwards. So this is for 8.3.1. Okay, so we're gonna say first of all, let's calculate our total resistance. Okay, it will help us to calculate the resistance of R. So our total resistance is R is therefore total voltage over total current, right? So what is our total voltage? We are told when switch S is closed, voltmeter V2, which is there, which is the total voltage is 8.8, divide by the total current, which is 0. We solved it there, 0.8. Put that in a calculator. It's 8.8 divided by 0.8. We get 11. Okay, we don't have to put units now because we're still solving. While you're still solving, you don't have to put units. You can only put units at the end. Alright, so we've got our R total. How's that going to help us? It's going to help us here, because now that we know our R total, then we can say 1 over R total is equals to 1 over I'm gonna say R, the R they want us to calculate, plus 1 over 4 plus 8, which is 4 plus 8, which is 12. And anyway, I'm going to put this in a calculator. So 1 over R total is 11, is equals to 1 over R plus 1 over 4 plus 8 is 12. And then I'll have that 1 over R is, I'll take this one that side, so I'll have 1 over 11 minus 1 over 12. Okay, so what I want to do is put this in a calculator. I'm just going to say 1 over 11, go to the side, minus, put 1 on top, and I put 12 here. What do I get? So 1 over R is equals to 1 over 132. Well, just so works out that R then is equals to 132. Now I have to put my units, which is ohms. There we go. Cool. Now let's say this is now question, let's go purple, question 8.3.2 says the battery becomes heated when voltmeter V2, okay, over there, is replaced by connecting a wire. Explain this observation. So we connect a wire over there. Let me simulate that for you so that you can see what's going on. So as you can see here, there is our 10 volts battery, our resistance of 4 volts, 4 ohms, and our resistance of 8 ohms, and our current of 0.8. well, it just worked out to be 0.83, but fairly much. So let's see what happens now. I have a wire that I've put there, I've not connected it. And now this question is saying, let's say I connect that wire there. Okay, see what happens. The battery is burning up. Okay, but now let's see what's actually happening. Let's cut that connection there. Let's join those. What I want you to see, look at this ammeter, the reading of the current. Okay, it's joined. You see that the current is astronomically high. So what's happening is that there's an increase in current. Okay, and this is what we call a short circuit. And because there's an increase in current, the battery heats up. So let's go right there up. So we're going to say the wire replacement was running out of space. Anyway, you can see that that's replacement. The wire which is placement will increase the current, okay, coming into the battery. Into the battery. Thus short circuiting. I love the word thus, I don't know why. Thus short circuiting. Okay, the increased current, therefore, or let me just say therefore, comma, the increased current causes the battery to heat up even as, I want you to see something else here. Okay, what do we call these things? These are electrons. Okay, these are electrons, because if I check there, this is conventional direction, but these are electrons that are actually moving over there. Let me cut that. Okay, no, these are the electrons. You can see they're charged. So what happens when I connect, the electrons are moving slowly right now, but as soon as I connect, look at the electrons there, they speed up, and the speed heats up the wire and the battery. Okay, so I'm gonna say even as the electrons speed up, even as the electrons speed up, causing the battery to heat. The bigger the speed of the electron, as you can imagine, they cause heat. Okay, well, I think that's the last question. That's it from me. I hope you understood. Please do like and subscribe to our channel if you liked this content. This will help you to get notification for our future uploads, as we upload it very often, and also it will help others to access this information when they need it. Okay, so other than that, that's it from myself. I hope you enjoy the rest of your day, and I appreciate you.
Hello everyone and welcome to MB Tutors. I'm Tilo and I'll be looking at question 9 and 10 to follow soon. I hope you've enjoyed watching other questions, especially now that you're preparing for your exams. So yeah, please don't forget to like our videos and subscribe to our channel, and please don't keep this information to yourself. Do tell others. Alright, let's see what is happening in question 9. Alright. So, the simplified sketch of an electric motor is shown below. Alright, we have a commutator, carbon brushes, magnets, a pivot. Alright, and 9.1.1 asks, write down the energy conversion that takes place in a motor. Okay, so we have either a motor or a generator. Okay, if you don't know which one does what, if you don't know what a motor does, you must know. If you're living in South Africa and you've experienced load shedding, you should know what a generator does, okay? Generator provides electricity, and how does it do that? We go from mechanical to electrical. So if that is what a generator does, the motor does the opposite. So a motor converts electrical energy to mechanical, and hence we have motor cars. Okay, so in this case, because we have a motor, the energy conversion would be electrical to mechanical. Okay, to mechanical. And then 9.1.2. Okay, now is the motor above an AC or a DC motor? Okay, so how do we tell the difference? Okay, here we have a commutator, all right? If you have a slip ring commutator, or slip ring commutators, or yeah, slip rings, basically, they are slip rings, then you would have an AC motor. Okay, with the DC motor, I hope you can see in the sketch there that it is a split ring commutator. The ring is split. So if you have a split ring commutator, then we are dealing with a motor. All right. Sorry, we're dealing with a DC motor. Of course, we're dealing with a motor, but this would be a DC motor, not an AC. Okay, AC, slip rings. DC, split ring. Okay, so this is a DC motor. And if you would like to know more about this section, obviously you can visit our YouTube page and look at the videos there under the physics. If you go to playlists and go to physics lessons, you would see that we do cover it. Electrodynamics simplified. Just click on it and you'll see my husband there.
Whenever I right field, I forget.
Yeah.
And then the I now
Okay, now how do we
stands
stop this?
for current.
Oh snap. Okay, so yes, basically that's how you go to it, and that's how you get to see the lessons. All right, so it is a DC motor. Okay, 9.1.3. What is the function of the commutator in this motor? What does it do? Okay, so this commutator, you have your carbon brushes there on the side. I'm just going to write it down quickly and then we'll discuss briefly. Okay. Alright, so basically the function of the commutator is to allow the current to flow through the coil of the wire. Okay, and an important thing to mention is it allows that current to flow in one direction. Now you would know with an AC motor, an AC generator, the current can flow in either direction, okay? Backwards, forward, whatever. But with a DC motor or a DC generator, it has to be in one direction. Okay, so that is the function of the commutator. And then we get to the question, the calculations. 9.2. So a resistor Y is rated 220 volts, meaning if you were to put a voltmeter around that resistor, which they've done there, you would get a rating of 220 volts. A reading, not a rating. And then it has 100 watts, meaning the power is 100 watts. And it is connected to a 220 volt alternating current source, as shown in the diagram below. Okay, so now for 9.2.1, they would like for us to calculate the resistance of resistor Y. Okay, so this is where now we deal with the root mean squared, so IRMS, VRMS, okay, and then you can have a look at the equations that you are given. So in this case, what do we have? We have the power, okay, in this case it would be average power, so that's 100 watts, and then we have the voltage, the RMS voltage, okay, and that is 220 volts. All right, and now we are looking for the resistance. Okay, so we're going to have a look at our equations of not equations of motion, but our equations to just have a look which one would be applicable in this case. Okay, so we have the power, the average power. We also have voltage and we're looking for resistance, and you can see the equation there that we're going to use, which is basically the average power. Okay, so P average is equal to V squared, and that voltage is RMS voltage all over R. And if I make R the subject of the formula, well, we're going to get VRMS squared all over P average, or AVE. AVE. Okay, and what is our voltage? Well, 220 squared, and our power is 100. Right. Let's just go back to the question and just make sure we have the right, the correct stuff. Okay, we don't want to be doing wrong things. Yes, it's 100 watts. And so we're going to calculate quickly. What is 220 squared? All right, divided by 100. And that's basically 484. And what is the unit? Well, we're dealing with resistance, so it's ohm. Okay, 484 ohm. And now we get to 9.2.2, and we're almost done, guys. Thank you for sticking through. 9.2.2. Calculate. Okay, we haven't even read what it's saying. So it says another resistor Z with a rating 220 voltage. Okay. Then we have X amounts of watts. It's now connected in series to resistor Y. Okay, we've been dealing with resistor Y. All right. And to the same AC source. All right. And then we have the current below. Now the power dissipated by resistor Y changes to 80. So initially we had 100 watts and now we're on 80 watts. But the resistance remains constant. Okay, so I'm just going to redraw this again, or attempt to redraw so that we can put in the information that we know. Okay, so there we have, okay, you know what, now I am wasting time unnecessarily. Okay, so let me just read the question. It says calculate the power rating X of resistor Z. Okay, assuming that resistor Z has constant resistance. Okay, so something is happening with my tablet. I'm just gonna pause a bit, wait for it to think about what it wants, and then we'll continue. Alright, so my tablet is done thinking. Alright, so now we need to get the power, alright, across resistor Z. Okay, so what do we know about resistor Y? We know the resistance we calculated is 484 ohm. The power is 80 watts. And now how are we going to get the power through Z? We only know the voltage there. It's 220 volts. Okay, so yeah, VRMS. RMS. So I am supposing or suggesting that let us find the current that is flowing through this circuit. And what will that do for us? If we get the current flowing, we can then be able, through the equations given to us, calculate the power, thereby resistor Z. And what are we going to use exactly? Which equation will we use? All right, so how will I get current? We have 3 equations that involve current. Okay, or maybe just 2. Yeah, 2 in order for me to get current. Okay, so I could use the average power. Let me just take this up. So we have the average power, which is equal to VRMS times IRMS. And basically, for us to get our IRMS, we're going to take the average power over VRMS. Okay, we can use that equation. And then secondly, we can use the equation again P average is equal to I squared RMS times R. Okay, why am I giving you all these options? Why couldn't I just choose one equation and we go with it? I wanted to see and to show you, or for us to see which one would actually be correct. Okay, so this is the first one. Let's see, will they give us the same answer? Okay, if I write this in terms of RMS, I would have the average power over the resistance and I would root it. Okay, so we are going to calculate. There's also a third option, guys. I don't know if I would be incorrect in mentioning it, but we do know that voltage is equal to current times resistance, right? So therefore, resistance would be voltage. No, current would be voltage over resistance. So we have three options. My question is, which one is the right equation that we should be using? But let's just calculate and let's see. Okay, so the average power, listen, we are calculating the current because we have more information from resistor Y. So just be careful of that. We are looking at resistor Y as we're calculating this. So the average power there is 80. It reduced from 100 to 80. And the voltage, the voltage, let's say it's 220. Okay, so we get a current of 0.36 amperes. Okay, if we now take the root of the average power, which is 80 over the resistance, which is 484, we get an answer of 0.41 current, ne? Yes, amperes. And lastly, what if we say the voltage over the resistance, which is 484? Yes. 484. I'm doubting myself now. Ooh, we have 0.45 amperes. Imagine this is you. This is an exam. You decided to take one equation and you get one answer and you're like, let me just check out that other equation. You get a different answer. And you're like, what's going on? Okay, guys, in this case, it would be an error, okay, for you to go with this and to go with that. Why? Remember when the voltage across resistor Y was 220 and your power was 100, you got a resistance of 484, okay? But now, since the power reduced from 100 to 80, you don't have 220 VRMS anymore. It has changed, okay? So you'd have to use this equation, VRMS is equal to R times P average to get the new voltage. So what is incorrect here is the voltage that we used, which was 220. It's not 220 anymore. It's going to be something else. And if you want to know what that something else is, you would basically take your R, which is 484, and multiply it by your P average now, which is 80. Okay. Yeah, 484 times 80, and then you root it. Okay, it's equal to that, and then you root your answer. So the new one would be 196. And therefore, if you used 196, surely you could have gotten the correct answer. Ne? This is me hoping for the best. So, yes, 0.41. So you would have to change first the VRMS. Do not use 220 because things changed. Conditions changed. Okay, so the equation I would really go for, if you want to know which equation you should go for the equation where the values that you substitute are values that you are sure of. We are sure of the P average, all right? It is 80 watts. We are sure of the resistance because they said it didn't change, which is 484. Or provided you actually got 484 in your previous answer. And this is definitely the answer that we will be going for. All right. And are we done? No, we're not. So we basically got the current going through resistor Y, and because we have resistors in series, the same current will go through. We don't have them in parallel, so that's good. It complicates our lives less. Actually, our lives are not complicated by it at all. So now we have the current flowing through resistor Z. Now how are we going to get the power? We go back to our equations and we say, okay, I can use P average is equal to V RMS times I RMS. That is the one that I would go for. Why? We've been told that the voltage around resistor Z is actually 220, so we can actually use the 220 there, and we have just calculated I RMS, so we can use that. Can we use the second one, I squared RMS times R? We don't know what that R is, we don't want to play games. And then the last one, V squared RMS over R. Again, we're not really sure what R is, so the first equation is what we're going to go for. Okay, so the average power will be equal to V RMS times I RMS. Okay, and what is V RMS? It is 220. What is I RMS? It's our rounded off value, 0.41. Okay, let's see what that value will be. So I have 0, I'm going to use this one and multiply it by 220. So I get 89.44. So we have 89.44 watts. And from there you can take your P average if you're really interested in knowing what the resistance is. You can use the equations to get the resistance, because you have V RMS, you have P average, you can get R. Okay, and I think that's it for question 9. Let's just make sure. Yeah, calculate the power rating X. Yeah, we're basically done. Thank you for tuning in. See you at question 10. Hello everyone and welcome back to MV Tutors. I'm Tsolo and I'll be looking at question 10 with you guys. The final question. So it is the photoelectric effect. I had one person ask me in the comment section, they were saying, is the photoelectric effect section taken out? I do not believe it is, because as you can see it was written, so please do study it. As far as I know, only in chemistry the fertilizer section has been taken out. I don't think it's back yet, but we'll see with paper 2. Anyway, 10.1. The apparatus illustrated in the simplified diagram below is used to demonstrate the photoelectric effect. Okay, so basically with photoelectric effect, you have incident light, and if it has enough frequency, it can start to charge up the electrons, and with more energy supplied to the electrons, they can start moving, okay, and have kinetic energy. Okay, so now 10.1.1, it asks, what or define the term photoelectric effect. And guys, I will keep on referring you to our videos because we took some time making them so that you can understand what's going on. But if you want to know what's happening,
so we have defined the work function as Planck's constant times.
Where's this thing playing? Okay, I'm just going to get it quickly and then we'll go through the term. Yeah, and there we go, guys. It's written quite small so that you can go to the video and check it out. But basically, the photoelectric effect is a process whereby electrons are ejected from a metal surface. So if you know with metals, you know that there's a sea of electrons around the metal, okay? So if you shine a light on it with enough frequency, it can eject the electrons from the metal surface, and with more energy it can make it move. So it's a process whereby electrons are ejected from a metal surface when light of suitable frequency is incident on the surface. That's basically the term photoelectric effect. Okay, if you want to know more about it, please do check out the video. It's quite short, well, depending what you define as short, but you'll definitely understand what's happening. So yeah, we are done with the definition. And then 10.1.2, Now, yeah, calculating. I love calculations. So, calculate the number of photoelectrons emitted in 1 second if the total energy transferred by the light to the metal plate per second is 1,75 times 10 to the negative 9 joules. Okay, this question can be a bit loaded. We are looking for the number of photoelectrons. If you go back to your static electric section, you would know that if you want to calculate the number of electrons, you would have to get the charge of the electrons. The charge that we have calculated and divided by the charge of an electron, and you'd get the number of electrons. In this case, what are we gonna do? Because all we have is energy. Okay, so we're basically, for us to get the number of electrons, we're gonna basically take the total energy. They've given it to us as 1,75 times 10 to the negative 9, and we are going to divide it by the energy of each photon, because remember that light has dual nature. Okay, it first has the wave action part of it, and then it has the particles. All right, so as the light shines on a metal and it releases or ejects the electrons, provided it has sufficient frequency, it takes up one electron at a time. Okay, so there's a packet of energy for a certain electron. And if you look at your equation, that packet of energy, so basically the energy of a photon, okay, just take this up. So the energy of a photon is basically equal to there are various equations here, but the energy of an electron is basically equal to Planck's constant times the frequency. Okay, again, if you refer to the video that I made, you will see that I actually put the E photon so that you know the energy of a photon or photoelectron. Okay, so now Planck's constant, we can read it out here, which is 6,63 times 10 to the power negative 34 joules per second. And then we have been given the frequency. They gave it to us. It says incident light of frequency 1,2 times 10 to the 15 hertz. Okay, 1,2 times 10 to the 15 hertz is shone. All right, so we're going to get the energy of a photon. All right, I am hoping that this calculator gives me answers in scientific form, or else we are a bit screwed. Negative 34. All right, oh yeah, it does give in scientific notation. That's good. 1,2 times 10 to the power 15. And then we get, put in the right things. We get 79,56 times 10 to the negative 20. Okay, so that's just the energy of the photon. Now we need to get the number of electrons. So let's just go back to our original equation. We have the total energy, which is 1,75 times 10 to the negative 9. And the energy of a single electron, that's 79,56 times 10 to the negative 20. And then finally, our answer will be equal to, so we take 1,75 times 10 to the negative 9 divided by the answer we got previously. Why? Okay. All right. This is the answer that it gives. It's fine. We can do this. I have 2,2. Okay, 2,20 times 10. Now let's count. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's times 10 to the 9. They're like 2,2 billion, almost at million. Times 10 to the 9 is billion. So we have 2,2 billion electrons. All right, so we are done with question 10.1.2, and now 10.1.3. So, calculate the maximum speed of a photoelectron if the threshold frequency of the metal plate is 9,09 times 10 to the 14. Remember, the threshold frequency is the minimum frequency that is required to get the electron a little bit excited for it to, just to wake up a bit, and then it can move eventually as you provide more energy. Okay, so yes, now let's go to our formula sheet. And we go back to the energy of a photon. So, okay, so we have E, the photon. Now, because we're dealing with kinetic energy, we're going to take the other equation, which is equal to the work function plus the maximum kinetic energy. Okay, so we are looking for kinetic energy. So I'm going to say the kinetic energy, the maximum, is equal to the energy of a photon minus the work function. Now, what is the energy of the photon? We actually calculated it last time. It is 79,56 times 10 to the negative 20. Okay, and then we're subtracting the work function. What is the work function equal to? It's equal to Planck's constant times the threshold frequency. We need to go back to the question to check out what the threshold frequency is. But while we're passing, let's just put in Planck's constant, 6,63 times 10 to the negative 34. And then we're going to multiply it by, so remember, work function is the threshold frequency times Planck's constant. So the threshold frequency that they gave us is 9,09 times 10 to the 14. Okay, and so we can get the kinetic energy, the maximum kinetic energy. So I have 79,56 times 10 to the negative 20, and I'm subtracting 6,63 times 10 to the negative 34 times 9,09 times 10 to the 14. Oh, because this why? Oh, okay. Can come down. There it is. I have 19,29 times 10 to the negative 20. And that is joules. Okay, they did not ask us for the kinetic energy. They asked us for the maximum speed. So we're basically looking for V. All right, so what is the equation for kinetic energy? It's basically half m v max squared. Okay, so for me to get the maximum velocity, I would say 19,29 times 10 to the negative 20. All right, I'm multiplying that by 2, because if I take half to the other side, it becomes a 2, and I am dividing it by the mass of an electron. What is the mass of an electron again? It is 9,11 times 10 to the power negative 31. Yeah, basically that. And then all of this is rooted, because remember we had V squared. Okay, so let's just take it a bit up. Let's get the calculator out and see what we can do. So we have root, I'm going to take that answer, I'm going to multiply it by 2, and I'm going to divide it by the mass of an electron. Alrighty, and then the answer is, they move. 650,817,27 meters per second. They're quite fast, hence we can't see them with the naked eye. they're so minute as well, so we can't really see electrons. All right, and then now 6.2, no, 10.2. Briefly explain how an emission spectrum is formed in terms of energy transitions. I will again refer you to our lesson where we describe, or we actually explain, the emission and the absorption spectra. Okay, so if you do check the video out, you'll see that I do describe the continuous spectrum, emission and absorption. But since they're asking to say, briefly explain how an emission spectrum is formed in terms of energy transitions. Okay, firstly, when you form an emission spectrum, basically that's when you have a gas that is heated and the electrons absorb the energy and then they move to higher energy levels. That's just the basic definition of it. If you want to know more, you can go further. I have a table there that pretty much summarizes the difference between emission and absorption spectra. Okay, and basically with the line emission spectra emitted by hot gases under low pressure, the energy is emitted in a form of a photon, and then it's emitted by exciting atoms which make transitions from higher to lower levels. Okay, so as it releases the energy, it then goes to lower energy levels, but when it absorbs the energy, it goes to high energy levels. But yeah, this is just 2 marks in this question, so the initial definition I gave you there at the beginning, that would suffice. And that's it from me. All the best with your exams. If you have any questions, queries, criticism, whatever that can assist us to be better and to also assist you better, please do write in the comment section below. Otherwise, don't forget to like and subscribe. Bye.